Hi, and welcome to this talk on reflection. Reflection is a form of scattering. What we're talking about in this talk is a particular scattering problem that has broad relevance in propagation theory and engineering. Specifically, the topic is scattering of a plane wave from a planar boundary between two semi-infinite material regions. And I'll show a picture of that in just a moment. In this talk, we'll talk first about the normal incidence case, in which a plane wave is incident upon the planar boundary in the direction perpendicular to the boundary. This will quickly lead us to the idea of a reflection coefficient, which quantifies the strength of the reflected field. Then we'll talk about oblique incidence. We'll talk about the curvature of the reflected wavefront, and we'll talk about Snell's law, which tells us the direction of the reflected wave. We'll stop short of talking about the reflection coefficient for the oblique incidence case. That's a bit more involved and will be covered in a later lecture. Finally, we'll talk about the principal limitation of the theory discussed here. That limitation is that material boundaries are always finite, and the presence of edges in the surface leads to something more complicated than mere reflection, namely diffraction. Before getting started, just one more brief comment. What I'm going to discuss in this lecture appears in any good textbook on electromagnetics. The citation at the bottom of this slide is just one suggestion. If you're interested in any details about what's going on in this lesson, that would be a good place to look. Okay, here's our starting point. Here we have a plane wave described by its electric field intensity vector, E super I. E super I is incident on a planar boundary between two media. These media are described by the wave impedances, eta sub 1 and eta sub 2, as indicated in the lower right. We say these material regions are semi-infinite. By this we mean that they extend to infinity in every direction, except along the planar boundary where they meet. The question now is, what happens when this plane wave reaches the boundary? It doesn't take much imagination to see that in this case we're going to have a plane wave which is reflected at the interface and also a plane wave which continues past the interface into the second material. This much you can see just from the symmetry of the problem. There's no reason to expect waves traveling in any other directions, and there's no reason to expect waves which are not plane waves. We'll call the reflected waves E super R, and we'll call the wave that continues into the second material E super T. Now, we want to figure out what is E super R in terms of E super I. In other words, how do I calculate the magnitude and phase of the reflected wave in terms of the magnitude and phase of the incident wave? Clearly, these waves are related by material parameters, so we're really looking for an expression containing values of eta sub 1 and eta sub 2 that give us E super R in terms of E super I. The trick to figuring this out is to invoke a boundary condition. That is, some mathematical statement that we know to be true along the planar boundary. To set this up, let's define E super I at 0 to mean the value of E super I at the boundary. Similarly, let's define E super R at 0 to mean the value of E super R at the boundary. And similarly, E super T at 0 means the value of E super T at the boundary. So, now, what do we know about these quantities? We know that the total field on the left side of the boundary is the sum of E super I at 0 and E super R at 0. And that's the left side of the equation I'm showing you now. And we know that the total field on the right side of the boundary is just E super T at 0. That's the right side of the equation I'm showing now. And, also, we know that these two total fields are equal at the boundary. Now, how do we know that? Well, it's because there's nothing present at the interface to create a discontinuity. That is, we know that a discontinuity in material parameters is not sufficient to create a discontinuity in E. Specifically, to create a discontinuity in E, we need a source, like charges or currents, and they are not present in this problem. The same reasoning gives us a similar expression for the magnetic field intensity, H. Now, we can convert the second expression into another independent expression in terms of E. To do this, we use our knowledge of eta sub 1 and eta sub 2 and the fact that E cross H points in the direction of propagation. Those two facts are enough to let us convert this second equation into an expression in terms of electric field intensity and the material parameters. I'm not going to show the math, but again, you can see the details in the reference I suggested earlier. Instead, I'm simply going to point out that we have two equations which will allow us to solve for E super R at the boundary relative to E super I at the boundary. And here's that result. We find that the ratio of E super R at the boundary is equal to eta sub 2 minus eta sub 1 over eta sub 2 plus eta sub 1. And we give this quantity a symbol. We call it capital gamma sub 1, 2. Gamma sub 1, 2 is known as the reflection coefficient. To get the reflected field at the boundary, we multiply the incident field at the boundary by this quantity. Now, before proceeding, take note. The reflection coefficient, gamma sub 1, 2, relates fields and not power densities. This is a common pitfall. Remember, the electric field intensity has voltage-like units, that is, volts per meter, whereas power density has power-like units, specifically watts per meter squared. So, power densities are related by the square of gamma 1, 2. The reflection coefficient gamma sub 1, 2 can be calculated in many different ways. Some of those different ways are more convenient if you know you are working with particular types of materials. In this slide, we're considering non-magnetic and non-conducting material. Non-magnetic means that the permittivity, that is mu, is equal to its free space value. And non-conducting means that the conductivity is 0. For such a material, the only remaining unfixed material parameter is the permittivity, that is epsilon. Now, this is a pretty good description of many commonly encountered materials, especially materials commonly encountered in propagation problems. We're talking about materials like brick, glass, and so on. So it's useful to have an expression for the reflection coefficient that's specific to this case, since such an expression would be entirely in terms of the permittivities of the two materials. This slide shows you how to get that expression. Equation 5.25 shows you what you get after substituting the square root of mu over epsilon for eta. Now, to make this expression even more convenient, we can express the permittivities in terms of relative permittivities. That is, 1 for free space, and so on. This is easy to derive because all you need to do is divide the numerator and the denominator by the square root of the permittivity of free space. And the result when you do that is equation 5.26, shown in the box at the bottom of this slide. Now remember, this expression is specific to scenarios where both materials are both non-magnetic and non-conducting. Okay, now for an example. We're going to consider reflection of radio waves from the surface of the moon. This example fits our assumptions very well. Any wave radiated by a source near the Earth will appear locally planar by the time it reaches the moon, so the plane wave assumption is valid. Not perfect, but certainly good enough. Also, the surface of the moon appears to be locally planar to such a wave. Again, not perfect, but a serviceable assumption at radio frequencies. It turns out for these kinds of problems, the surface of the moon is pretty well modeled as a homogeneous, non-magnetic, non-conducting material with a relative permittivity of about 3. This is enough information to work out the reflection coefficient. Here's the calculation. It's just a matter of plugging in values to the expression on the previous slide. You find gamma sub 1, 2 equals minus 0.27. This means that the magnitude of the reflected electric field intensity is equal to 0.27 times the magnitude of the incident electric field intensity. The minus sign means that the orientation of the reflected field is opposite the orientation of the incident field. This normally happens whenever you encounter a material that has higher permittivity than the one you started in. From this point, you can easily calculate the amount of power reflected from the surface of the moon. This is simply the square of the magnitude of the reflection coefficient. In this case, gamma sub 1, 2 is minus 0.27, so the square of the magnitude of the reflection coefficient is 0.07. In other words, the moon reflects about 7% of the power that's incident upon it. Now you might ask what happens to the other 93% of the power. Well, that power ends up inside the moon. And the moon is pretty big, and even though it is not very lossy, there is enough loss that the power eventually gets dissipated. In other words, you don't see the power reappear on the other side of the moon. Okay, now to increase complexity slightly. Let's consider a plane wave that is obliquely incident. That is, a plane wave which is incident from an angle psi super I relative to the normal, where psi super I is not necessarily 0 as it was in the normal incidence case. The first thing we need to establish is the kind of wave that we see upon reflection. Now, it might seem obvious to you that we should expect that the reflected wave here is also going to be a plane wave, and you would be right, but this is not quite as obvious as it was for the normal incidence case, so let's think about this for just a moment. One way to sort this out is to think of each point on the phase front as having a pointing vector attached to it. And we can imagine what happens as the phase front propagates. We would see that each pointing vector would trace out a path, and we would call that path a ray. So we can think of the phase front as a bundle of parallel rays, each representing a pointing vector, and each ray standing in for the pointing vector, all pointing in the same direction. So now we invoke symmetry again. Since the surface is flat and infinite, each ray must do precisely the same thing. That is, symmetry requires that each ray of the reflected field must be parallel to all the other rays of the reflected field. And if those rays are all traveling in the same direction, then we once again have a plane wave. In other words, symmetry again tells us that even in the oblique incidence case, the reflected field is a plane wave. Yet another way to say this is that wavefront curvature is preserved in reflection from a planar surface. However, we don't yet know for sure what the direction of the plane wave is. In other words, what is the angle psi super r as shown in the diagram? Now, you might suspect that psi super r equals psi super I, and you would be right. But this actually takes a bit of work to prove. The way to prove it is to again use a boundary condition. In the general case, this gets a little messy, so I'm going to show you how this works for a case where the work is relatively simple. That case is the one where the second material is a perfect electrical conductor, that is, PEC. We know that in a PEC, the electric field intensity must be identically 0. Therefore, the tangent component of the electric field intensity along the boundary must be 0. The normal, that is the perpendicular component of the electric field intensity, can be non-zero along the boundary, but the tangent component has to be 0. Now let's call that tangent vector the vector t hat, shown as the blue arrow in this diagram, and we'll call that the tangent vector. And let's consider a point of incidence called Q. Now, we can write a boundary condition for the total field at Q, and it's simply the one shown here. Namely, the total field at Q is the sum of the incident and reflected fields at Q, and we know that the tangent component of that total field must be 0, because the second material is PEC. Now once again, I'm going to skip all the math, but the procedure is straightforward. You simply substitute expressions for the electric fields and evaluate. What you find is that for this boundary condition to be true at every point on the surface, there is only one possibility, and that is that the angle of reflection equals the angle of incidence. Psi super r equals psi super I. For any other choice of psi super r, you find that you are unable to satisfy the boundary condition that the tangent component of the electric field must be 0 at all points on the surface. Now it turns out that essentially the same procedure gives us the same result, even if the second material is not PEC. The procedure for the non-PEC material case looks a lot like the procedure we just used to get the reflection coefficient in the normal incidence case. You simply get equations for E and H at the boundary by requiring the fields to be continuous across the boundary. You bring in the material parameters by expressing H in terms of E, and then you find that you can only solve the equations if the angle of incidence equals the angle of reflection. Now, when the smoke clears, the result is this. Regardless of the materials, angle of reflection equals angle of incidence. Again, for the full mathematical details, refer to the textbook I cited at the beginning of this lesson. By the way, this result is often referred to as Snell's law. Also, the same result can be derived in a different way using a principle known as Fermat's law. In all cases, you find that angle of reflection equals angle of incidence. Now, the last order of business is reflection coefficient for oblique incidence. Recall that we were able to obtain a simple expression for the reflection coefficient for normal incidence. This is not going to be possible in the case of oblique incidence. The expressions are going to be complicated. One reason for this is that in oblique incidence, the orientation of the electric field vector matters. This is not the case in the normal incidence case, because in that case, any possible orientation of the incident electric field is parallel to the boundary. In the oblique incidence case, however, all, some, or none of the electric field may be parallel to the boundary, and we need to account for that. So, we'll have to leave that issue for a later lesson. There's actually one more issue that we would like to address, and that's this. No boundary is infinite. For example, if we're talking about scattering of a radio wave from the wall of a building, what should we make of the fact that the wall is finite and doesn't extend to infinity? If the boundary is finite, we cannot expect to see reflection and nothing else. The other thing we should expect to see is diffraction from the edges of the boundary. Usually the situation is this. If the size of the boundary is large compared to a wavelength, then the scattering is usually well approximated as reflection, as described in the previous slides. Plus, perhaps a small amount of diffraction from the edges, which is often, but not always, negligible. The reflection in this case is referred to as specular, which basically means that the scattering we see is similar to what we predict for a boundary of infinite size. As the size of the boundary decreases, as that boundary reduces in size, the diffraction becomes more important. In fact, diffraction is the only way that you can account for the field in shadowed regions where there should be no reflection at all. Once the size of the boundary gets down to a few wavelengths, it's not possible to discriminate between specular reflection and diffraction. They basically merge into one scattering mechanism that is hard to describe in terms of simple geometrical contributions. Okay, time to review the main points. This lesson has been an introduction to reflection, specifically the scattering of a plane wave from the planar boundary between two semi-infinite, or at least very large, material regions. For normal incidence, we worked out the reflection coefficient, which in general is a function of the wave impedances of the media, and in the special case of non-magnetic and non-conducting media is a function of the relative permittivities. For oblique incidence, we worked out that the reflected wave is also a plane wave, and that the angle of reflection is equal to the angle of incidence, Snell's law. We did not work out the reflection coefficient, because that depends on the orientation of the electric field vector relative to the boundary. So we're going to come back to that later. Finally, we noted that in practical work, where the boundaries are finite, you may need to account for diffraction. And if the surface is not large relative to a wavelength, you may not be able to model the scattering as a sum of reflection and diffraction, as we have suggested here. That concludes this talk on reflection. Thanks for listening.